Hello everyone, welcome to exercise 5, Neural Networks. In this exercise, we will dive into universal approximation theorem and also the content of exercise 5. We know that in exercise 5, there are more NumPy. Since now you are familiar with the basic pillars of training a neural network, but different with the exercise 4, where you already have a simple classifier. In exercise 5, it's the code we release, and in the exercise document, it's more structured. In this way, you can get familiar with the basic models of the neural network project, and then trying to learn it in a more organized way. So first of all, here are some background info. Yeah, you may find currently from exercise 4, you are in a NumPy heavy part, since you need to reinvent the pillars of the deep learning. It means you basically rewrite every basic part of the neural network training project. But after exercise 5, actually there will be less NumPy implications, since we will introduce PyTorch, which is invented to help deep learning community to train their neural network easily. And exercise 6, you will have to learn some fine-tuning on higher parameters. But that is basically what you write in exercise 5. But we think currently the NumPy heavy work is still very important, since it can make you understand better how a basic neural network training code or project goes. So another thing is, for us, creating exercise is quite hard, and it would be really nice if we can get your feedback to it. We will consider your feedbacks too hard, but actually we cannot implement everything this semester due to the current resources, and also the feedback is welcome and important to us. We will, based on the feedbacks, to improve the course for the following semesters. So let's have a brief recap of exercise 4. In exercise 4, we already go over the pillars of deep learning, from data to model to the solvers. For the data part, actually for each deep learning project, it needs some data to do the training stuff. Those we need to define or to get a data set, and then with our defined function in the data loader, we get the data to the project, to the model, and then during the model, we need to write the neural network part. That's the most interesting part of the deep learning project. You can create your own one, and then you can actually just define those functions or the training objectives, and then to as the output, and then compare to the data labels we have in the data set. And for the solver part, we actually need some optimizers to optimize the weights of the neural network. And then for each training loop, we have the data in and then get output. We compute those functions, and then use the optimizer to optimize the network for one iteration. And for some iterations, we would have our validation set to do the validation to test how our trained neural network works for new data. When we back to the roads, actually, it can also be achieved by some common machine learning approach, like the SVM or the nearest neighbor. Like for the SVM, it's just project the data into a higher dimension space, and then it can be linearly separated by some functions. But what we do different is for the neural networks, it can have more nonlinear part that can be important to make it deep. So first, we want to show some basic conception of universal approximation theory. It's from several decades ago, and then it means for any continuous function of a complex set, there actually you can find one layer neural network that can only have a single hidden layer and an active function here. Take the sigmoid as example. You can also use others, and then this neural network can uniformly approximate the continuous space or the continuous function to within an arbitrary. Here show some examples like input, single input, and then with a one-dimension output, or you have the two-dimension input with some nodes in the hidden layer, and then you output the one-dimension number. And here, I'll defer to some proof. One is a readable proof, and the other one is a visual one. You can actually change the number or the parameters, the input, to the visual proof link, and then you can get some visualization of the output. You can have a better understanding of the universal approximation theorem if you are interested. And actually, here is a word of warning that for one layer neural network is not enough. For any deep learning project, we are actually to find the weights of the neural network from the training data. What we do so is the optimal goal or the ideal case is we find the surface or the function that can be can describe or the approximate the training data, but it's actually hard to find such weights since at the beginning you always need to initialize the weights of the neural network, and then through the gradient descent you need to find the weights in the end. But it's easy to become a local minimal, and then maybe it cannot handle to the new input. That means your trained neural network may be not that good to the other data. So that's why we introduced the deep learning or the deeper neural network compared to the one single layer. Here we call the shadow neural network here. The deep means it have more than one hidden layer. It may have two or even more, but there are some obvious questions. First of all, actually, do we even need the deep neural networks? The answer is yes, since when comparing to a single layer neural network, multiple layers allow for more abstraction powers given a fixed computation bucket. Means the neural network might have better generalization. For example, when we take a picture of the face, we want to recognize people. Actually, it's hard if you have only one single layer. Given the input, you only give an output of the whole face. It's actually hard to define. What we do is to have a multiple layer neural network. First, it can get some local features or the local descriptors like the mouth, the eyes. Every part can be different, and then following, and then you can get more structure of the whole face. In this way, the neural network can get more discriminative representations for the information from the input. That's why we actually need much deeper networks than a shadow one. So the second question might be why we do not just build a very deep neural network like 100 layers. The question is not that obvious. I mean, actually, there are some constraints. Imagine that you have 100 layers, and then each layer may have some a batch number of nodes, and then you can maybe need more memory uh, to save the weights of the neural network and then do the training. And actually, another thing is it's really hard to train a neural network with such deep layers. It may face some vanishing gradient stuff, and also deeper does not that means working better. Actually, for a deep learning project, it's not only concerning about the design of the neural network, it's actually also concerning about the data, how much data and what kind of data are you using to train the neural network, and also you need to fine tuning or tune the hyperparameters like the learning rate stuff or batch size. It's quite important in practice. And on the other side, designing a neural network that means only putting more layers or make each layer wider. It's not that simple. So yeah, but obviously we would say we need deep neural networks instead of like a single layer, but it's not simple to just stick the layers together to get a very deep networks to make it performance better. So let's dive into the exercise 5. First of all, we want to compare with the exercise 4. Since exercise 4, you already have an idea of how to train a simple neural network like a classifier of the house pricing. And in the exercise 4, you're actually using a small data set with a simple objective to discriminate the house is cheap or expensive, and with a very simple classifier with all input features like the different characters of the house, you can get a single weight matrix based on it and then get the output. And during the training, you use the gradient descent solver with the whole forward path in memory. In exercise 5, we use a server 10. It's actually have it's not like the housing price dataset. It's an image dataset. It containing 16,000 images with 10 labels. That's called server 10. It's actually an actual very competitive task to do the image classification, and Cypher 10 and also Cypher 100 is now still popular for the machine learning and deep learning community to train the new neural networks. Here we use Cypher 10 to do the training, and we also introduced the motorized networks with the chain rule. Compared with the simple classifier, here maybe the model become deeper, and then we want the gradient to be backward and forward and backward in a chain rule. Those we can stick those layers together. And also here we use a stochastic gradient descent. It's actually a very popular solver or the optimizer still using in the deep learning projects. In exercise 4, here you write everything together in the classifier class. Yeah, you do the forward and here, but it's actually quite simple, and it do not scale to some complicated projects with more layers or more functions. So here we follow the chain rules to do the motorization. here for the sigmoid class, here we actually write the forward and backward here to make the gradient to be forward and backward in a chain. You can do the optimization or the gradient descent in individually, and then make the two optimize together. So for the overview of exercise 5, different to exercise 4 have the two notebooks. Here we only have one notebook, but it's a quite long one. Here you need to implement some smaller implementation objective inside it. But for each one, actually you don't need to write it from the scratch. We already provide some very detailed instructions in the notebook, and then you can just try and follow the instruction here. And the deadline is next Wednesday, 4 p.m. And at last, also want to have a little bit outlook of exercise 6. We will use Cyberten again, but we will based on what you write here in the exercise 5 to do the tuning higher parameter stuff. It's quite actually important. Like in the left side, you can define the number of layers and also the neurons of each layer, and also the learning rate in the optimizer or the solver. Actually, you can decide it, and then during the you run the optimize during the optimization and namely the training. You can get a score of the both training and also the maybe the evaluation scores. You will find it very interesting that actually for maybe a fixed one side is how do you design the neural networks with such hyperparameters, and also the other stuff is the learning rate or the optimizer. When you change different numbers, maybe the results can be very different, and then yeah, you can try to make it funny to find the best solution of your problem. Yeah, that's all for the exercise 5. Then see you next week.